Imagine for a moment that you're on top of a foggy mountain, and your goal is to find the fastest path down to the valley below. But there's a catch. The fog is so dense that you can't see more than a few feet in front of you. So, how would you navigate? Well, one viable strategy would be to check the slope of the ground around you and take a step in the direction that appears to go downhill the most. After that step, you check the slope again and take another step in the direction of the steepest descent. You repeat this process until you reach a point where every direction seems to lead uphill, indicating that you have reached the bottom of the valley. In the realm of machine learning and data science, this scenario isn't just a metaphor. It's essentially how gradient descent, a cornerstone optimization algorithm, works. The mountain is a metaphorical cost function, a mathematical formula that quantifies how far off our predictions are from actual values. This cost function is what we're trying to minimize. Just like our journey down the mountain, our goal is to find the parameters for our machine learning model that gives us the smallest error, or, in other words, finds the bottom of our cost function valley. Just as with the mountain scenario, we begin with an initial guess, like standing at a random spot on the mountain. Then we iteratively update our parameters, or move our position on the mountain, to reduce the cost function, that is, move downwards, and the direction of the steepest descent. That's given by the negative gradient of the function at that point, which is why the method is called gradient descent. Now, in a high-dimensional space where our cost function could depend on many parameters, visualizing a gradient is a bit more challenging. In such a situation, you can think of a gradient as a multi-dimensional extension of a derivative. The gradient essentially points in the direction of the steepest ascent. Imagine it as an arrow on the ground pointing uphill. Therefore, to minimize the function, we should move in the opposite direction. Hence, the descent in gradient descent. But how much should we step in the direction of the steepest descent? This is dictated by a parameter known as the learning rate. Going back to our mountain analogy, the learning rate would be analogous to the size of the steps we take towards the valley. If our step size or learning rate is too small, it might take an eternity to reach the bottom. However, if our steps are too large, we might overshoot the valley and end up on another side of the mountain, possibly even higher than we started. Striking a balance here is crucial for the efficiency of the gradient descent algorithm. But how much should we step in the direction of the steepest descent? This is dictated by a parameter known as the learning rate. Going back to our mountain analogy, the learning rate would be analogous to the size of the steps we take towards the valley. If our step size or learning rate is too small, it might take an eternity to reach the bottom. However, if our steps are too large, we might overshoot the valley and end up on another side of the mountain, possibly even higher than we started. Striking a balance here is crucial for the efficiency of the gradient descent algorithm. Finding the perfect step size is akin to Goldilocks in the story of the three bears. Goldilocks didn't want her porridge too hot or too cold, but just right. Similarly, we don't want our step size too large or too small, but just right. If it's too large, we risk overshooting the minimum of our cost function. If it's too small, we could be waiting a very long time for our algorithm to converge. Just like Goldilocks, we need to find the step size that's just right for our purposes. At this juncture, you might be asking, how do we determine the right learning rate? The answer to this isn't straightforward, as the optimal learning rate can vary based on the specific problem, the cost function, the data, and even the specific iteration of the algorithm. In practice, finding the right learning rate often involves a bit of trial and error. You might start with a smaller learning rate and gradually increase it until you find a rate that allows the algorithm to converge efficiently. This process, while possibly a bit tedious, is an important part of ensuring the effectiveness of gradient descent. Now you might wonder, why is understanding gradient descent so important? Well, at its core, gradient descent is an optimization algorithm. And optimization is a critical aspect of many areas of science and technology. From designing aerodynamically efficient cars to optimizing delivery routes for logistics companies. Understanding how to minimize or maximize an objective function is crucial. In machine learning, selecting the right model, the right features, and even the right learning rate is an optimization problem. Here, gradient descent provides a systematic method for improving the model iteratively. It's like a guide, taking us through a foggy landscape of complex mathematical terrain towards our goal, the most accurate predictions our model can make. By understanding how gradient descent works, we gain a deeper understanding of the inner workings of the machine learning models that increasingly impact our everyday lives. Whether you're a data scientist working to improve your model, an engineer trying to optimize a system, or even just a lifelong learner trying to understand the technology that's reshaping our world, understanding gradient descent can provide a valuable perspective. After all, we live in a world full of hills and valleys, and knowing how to navigate this terrain is a skill that will serve you well in many areas of life.